Hi there. This video is going to be a quick introduction to the concept of atomic term symbols. This is what we use to account for all of the atomic spectral lines that you'll see in atomic spectra. So lots of unexpected splittings present in those spectra, and this is how we can account for all of those lines that we see. All right, so my first question for you as we get started is to ask you, how many different ways are there to place a single electron in 3 degenerate 2p orbitals? Okay, so take a second and see if you can think of a variety of ways that you can place that one electron in any of these 3 orbitals. Okay, so hopefully you probably started with maybe putting one in that orbital, okay? Or we could put one in this orbital, or we could put it in this orbital, or I could put it in this orbital spin down, or in either of the other 2 orbitals spin down. So hopefully you're getting the sense that there's quite a few ways that we can place that single electron in these 3 degenerate 2p orbitals. All right, so my next question for you after that is to ask you, do the quantum numbers that we assign to that electron change depending on how you place it? So take a second and think about that. Okay. Hopefully you took a second to think about your answer to that question, so let's walk through it. Well, first of all, let's remind ourselves what our quantum numbers are that we assign to an electron. So we have N, L, M sub L, and M sub S. Okay, so for all of the different options for placing this electron in those 3 degenerate 2p orbitals, okay, our N and our L, right, are not going to change, okay? So those, right, that's the 2p designation that we get, right? So we're always in some sort of 2p situation, no matter what we're doing up here, no matter where we're placing our electron up. What about M sub L? Okay, what does M sub L refer to? Okay, that's our magnetic angular momentum quantum number. Okay, so remember that's the one that essentially tells us the orientation of our orbital in space. So that would relate to our px, py, or pz designation for the p orbitals. Okay, so how we normally label that is by putting the M sub L value underneath the orbital location, so under these dash lines. So convention, we go negative to positive with 0 in the middle. So we would have one orbital assigned to M sub L minus 1, one orbital assigned to M sub L 0, and the third orbital gets assigned to M sub L plus 1. Okay, so it's totally arbitrary how we're labeling these. Okay, I could have done them in any order. It just is convention to go negative to positive and have the 0 in the middle. And also, it turns out that the M sub L equals 0 corresponds to the z coordinate. Again, just convention. Okay, so now let's ask ourselves the question again, do the quantum numbers assigned to the electron change depending on how we place it? Okay, so now looking at M sub L, we can see, having done our labeling here, that it does in fact matter how I place my electron. It matters if I place it in this orbital, or this orbital, right? Each one of those has a different M sub L quantum number associated with it. Okay, same with the M sub S, right? So if I am spin down, like I've drawn it here, that gives me a M sub S of minus 1/2. If I choose to draw it spin up, then I get an M sub S of of plus 1/2. Okay, so M sub L and M sub S both do change. Okay, so depending on how you've placed your electron in those 3 orbitals. Okay, so it turns out that each of those different quantum number assignments, each of those different ways that we put our electron into those orbitals has a different energy associated with it. Okay, so we need to have now a way that we can essentially notate or label what those different energies are. All right, and the way that we start getting at that is by essentially accounting for all of the various angular momenta that we have going on in our system. Okay, so remember there are 2 types of angular momenta that we are normally interested in, the orbital and the spin angular momenta. Right now we're going to ignore the nuclear spin. We already talked about that with its relation to NMR. Okay, so we'll stick with our orbital and spin angular momenta for the rest of our conversation. Okay, and it turns out that when more than one electron is present in an atom, okay, the total orbital and spin angular momenta can essentially just be added together. Okay, so you can add up all the individual orbital angular momenta and get a total orbital angular momentum for your atom, and you can do the same with the spin angular momenta. You can add up all the individual spin angular momenta for the electrons in your atom and come up with a total spin angular momentum. Okay, so L, capital L. Okay, again, notation is very important here. You really need to be careful about distinguishing between your different quantum numbers. Big L is very different from little l. Okay, so be very deliberate with the notation that you're using. Okay, so big L is our quantum number that represents our total orbital angular momentum of a particular state, okay, or in other words, a particular arrangement of electrons. Okay, and then capital S is the quantum number that represents the total spin angular momentum of a particular state or arrangement of electrons. Okay, so the values of our quantum numbers, L and S, are going to be, again, related to our M sub L and M sub S, just like we have for our individual electron labeling. Okay, so here we define big M sub L to be the sum of all of the little m sub L's for each electron in your atom, and then likewise big M sub S is going to be the sum of all of the little m sub S's for all of the electrons that are present in your atom. Okay, so these are essentially just like we had for little m sub L, the component of our total orbital angular momentum along the z-axis, okay, and likewise the component of our total spin angular momentum along the z-axis. Okay, and again we get possible values of big M sub L H bar, where M sub L can range from the values of minus L to minus L plus 1 all the way up to plus L. Okay, so hopefully you're seeing the similarity with what we've already talked about for our individual electron quantum numbers and how we label those. Okay, so here, again, when you're talking about multi-electron systems, we switch to the capital designation. So we get our capital M sub L's, capital L, capital S, capital M sub S. Okay, so that just indicates that you're talking about more than one electron that you are working with. Okay, so similarly for the spin, total spin angular momentum, okay, we get values of M sub S related to that quantum number that range from minus S to minus S plus 1 all the way up to S. Okay, so these values may take on non-integer values here, okay? And your m sub l's will generally be some sort of integer. Okay, so let's look at how we would approach this practically. Okay, so for 2 electrons, we're going to keep things simple to start with. So if we're just looking at 2 electrons with orbital angular momentum quantum numbers labeled L1 and L2, okay, the general rule for adding those angular momenta is something called a Clebsch-Gordan series, okay, where we can determine our total orbital angular momentum by adding up our individual angular momenta and following that range or that pattern of taking the sum minus 1, and then following that series until we truncate at the absolute value of the difference between the 2 quantum numbers. Okay, and similarly for our total spin angular momentum quantum number, okay, we can obtain that from a similar Clebsch-Gordan series where we use now the spin quantum numbers S1 and S2 for each individual electron in our 2-electron system in this example. So again, we start with the sum. Next term is the sum minus 1. Okay, then you keep going in that series until you reach the absolute value of the difference. All right, so sounds maybe a little bit abstract at this point. You'll get some practice at using this. So let's do a quick example, just determining the possible values of S for a 2-electron atom. Okay, so here we need the values of little s for our 2 electrons. So we know that S1 is going to be equal to 1/2. And likewise, S2 must be equal to 1/2, okay, because that's the definition of the spin quantum number for an electron. Okay, remember that back from our introduction to the idea of spin and our spin quantum numbers. Okay, so we are just going to do our Clebsch-Gordan series. So our big S is going to be the sum of S1 plus S2. Okay. And then S1 plus S2 minus 1. Okay, and then we could keep going. 1/2 plus 1/2 minus 2. And then we're going to truncate at 1/2 minus 1/2. Okay, so this is always the end point. Okay, I recommend that you actually figure this part out first. Okay, so you don't go too far and waste your time. So let's take a look at what options we have when all is said and done here. Okay, so we have we're going to truncate. We can see here at 0. Okay, so 1/2 plus 1/2 is 1. 1/2 plus 1/2 minus 1 is 0. So then we would start getting into negative ones, okay? And then we keep going to 0. But we know we truncate at 0, okay? So we're going to ignore everything that comes after 0. All right, so S then can have values, in this case for a 2-electron system, of 1 or 0. Okay, and those will, we'll see those values will end up essentially giving us different energies for different arrangements of these electrons in our atom. All right, so we're just starting off here by learning the mechanics of the tools that we need to be able to put everything together. Okay, so you might be asking yourselves at this point, why are we doing all of these random accounting and labeling of our electrons? What is all this work for? Well, it's allowing us to be able to put together a new system for labeling our various atomic states that we encounter for our atoms. Okay, so your next question might be, well, why do we need to have more labeling? I feel pretty good with our basic run-of-the-mill electron configurations. Those seem pretty informative to me. Well, let's take a closer look. All right, let's look at, for example, the ground state electron configuration for nitrogen. Okay, so nitrogen has 7 electrons, so your ground state configuration will look like 1s2, 2s2, 2p3. Okay, hopefully you're satisfied with that being the ground state electron configuration for nitrogen. Okay, so just like we did in our example starting out of this video, we can put those 2p electrons. So here, see, we've got 3 p electrons in those 3p orbitals, not a full subshell, right? So remember, we've got room for 6 total electrons in those 3p orbitals, okay, 2 per orbital. Okay, those 2p electrons, those 3 2p electrons can be in any of the 3 2p orbitals and have any spins as long as they're consistent with our Pauli exclusion principle, right? So we still can't violate our paired spins in one orbital. So they still have to be spin up, spin down if they are in the same orbital, okay? But other than that, they can occupy any one of the 3 orbitals, okay? So if you sat down and did an accounting of all of the different ways that you could put 3 electrons into 3 of those 2p orbitals, it turns out that you would end up with 20 different ways to put them in there. Okay, that's a lot of different combos. Okay, you can imagine how things get when we start getting into d orbitals and f orbitals and the number of options that you have for those. So it gets pretty overwhelming pretty quickly. All right, but 20 is pretty manageable, so we'll stick with this example. All right, so each of those 20 different ways to place your 3 electrons in the 3 degenerate p orbitals is called a microstate. Okay, so we've seen this term before. This is the same idea that we used when we discussed entropy in our thermodynamics class. Okay, it's just essentially different ways that you can put your electrons in your orbitals. Right, and they're not necessarily all going to have the same energy. We will soon find out. Okay, so let's look at a few of the possible microstates for nitrogen and assign the corresponding m sub L and m sub S, or big M sub L and big M sub S values. Okay, so I am just going to start doing a few options. There's, again, 17 more in addition to what I'm going to draw. Okay, so I'm going to do an option where I have 1 in each orbital and they're all spin up. Let's pair a couple on this example. And then maybe we'll swap those around a little bit. Okay, so you can see that I have a mix of different spin options, different pairing options. Okay, like I said, there's 17 more if you want to kind of practice or have a little meditation and see if you can figure out the remaining options to give you your full 20 different ways that we can put these electrons in these orbitals. Okay, but let's just look at these 3 for an example. All right, so we want to now assign the corresponding m sub L and m sub S values. So let's, again, just kind of make a little arbitrary designation here. And just to show you that it's arbitrary, I'm going to label it in a different way. But I still, creature of habit, like to put the 0 in the middle. Okay, so I just swapped my positive and negative. Okay, it's not going to matter because when all is said and done, when you account for all 20, okay, you're going to end up with the same result, no matter if you have this as -1 and this as +1. Okay. All right. So big M sub L. So make a little table over here. So we want a big M sub L and a big M sub S. So remember, there we are just, if we go back to our definition, where did we define it? Over here. Okay. Remember, these are the definitions of those big M sub L and big M sub S. We're just adding up the individual M sub Ls and M sub Ss. Okay. All right, so for this first example, our m sub l, let's add up all our little m sub l's. Remember, these are little m sub l's labeled down here. So we have +1, +0, -1. So if we add all those up, we get an overall m sub l, big M sub l of 0. Okay. And then likewise for the m sub s, big M sub s, we're going to add up all of the little m sub s's. So add up all the little spin quantum numbers. Okay, so it's a spin up +1/2, another spin up +1/2, another spin up +1/2. Okay, 3 times 1/2 gives us a m sub s of 3/2. Okay, so why don't you take a minute, pause the video, and see if you can assign the big M sub l and the big M sub s for these next two scenarios. Okay, so hopefully you took a moment to assign those yourself. Let's see how you did. Okay, so here we have 2 electrons and a +1, so we get a total +2 from that. And then we get a 0 M sub l from this electron, so we have a total of +2 for that M sub l. And then adding up our spins, okay, whenever you've got paired electrons, right, automatically going to cancel those spins out. Okay, so we get 0 spin from those paired electrons. We're left with 1 spin up, so that gives us a +1/2 M sub s for that. And then lastly, our M sub l's for this example. Okay, we've got +1 from this electron and 2 in our 0. Okay, so that gives us a total of +1. And then for the M sub s, again, these are going to cancel each other out. We're left with 1 spin down, so we get an M sub s of -1/2 for that. Okay, so hopefully you can start to see that the corresponding M sub l and M sub s values that result from these different arrangements of electrons in these orbitals are different. Okay, so these are going to lead us to some potentially different total energies that are represented by those microstates. Okay, and that is why we need a more detailed designation for the electronic states of our atoms than just our run-of-the-mill electron configuration representation. Okay, this just doesn't quite cut it in helping us to account for all of the different options for where our electrons can be in an atom. All right, so that brings us to the pièce de résistance of this video, which is the actual atomic term symbol that you're going to become acquainted with. Okay, so as we just talked about, we can have different couplings of those magnetic moments, your M sub l's and your M sub s's, okay? And those resulting energies for those different couplings will be different if your spins are in opposite directions in the same orbital, or in the same direction in different orbitals, or opposite directions in different orbitals, okay? Or in different M sub l orbitals altogether. Okay, so you're going to get a bunch of different types of coupling of those electrons in those various arrangements. Okay, what we want to do now is to essentially group all of those different kinds of arrangements into explicit energy levels. Okay, so some of those microstates, some of those individual arrangements of electrons are going to have the same energy. Okay, and some of them might be different. So we need a way that we can account for all of the different energies that arise from all of those different microstates. Okay, so if states that arise from the same electron configuration have the same value of L, big L, and the same value of big S, okay, then we can say that they have the same energy, okay, and are going to belong to the same atomic term. Okay, so this is just essentially the way that we can start grouping our different microstates by energy. Okay, and right now we're going to ignore what's called the spin-orbit interactions or the Russell-Saunders coupling. Okay, there's going to be another little bit that we add on later. Okay, for now we're just going to concern ourselves with the L and the S parts of our atomic term. Okay, so each term of an atom is designated by a term symbol. Okay, so remember now each term can house essentially more than one microstate. Okay, so because remember we've got all of those different m sub L's and all of those different m sub S's. Okay, those correspond to particular big L's and big S's. Okay, so the term symbol notation that you're going to be working with here is this 2s plus 1, okay, superscript, and then an L, okay, where L is, again, same as we've been talking about. L is the total orbital angular momentum quantum number, okay, and the big S is still our total spin angular momentum quantum number, okay. So we've already talked about how we get those. The 2s plus 1, okay, the special little superscript up here, this 2s plus 1 is called the multiplicity, okay, and we would name that as a singlet, doublet, triplet. Okay, you might have heard this vocabulary floating around in some other classes occasionally. Okay, and then, and it's very, again, notation matters. It's an upper left-hand corner designation, okay? You can't put it over here or down here or down here, okay? The positioning matters and has a specific meaning for us, okay? So again, be deliberate with your notation. Okay, and then this L, okay, you're going to sub in for this L the corresponding letter, okay? So this is just like how we get our little SP, D, and F orbital notations, right? Those each correspond to a little L number of 0, 1, 2, 3, 4, and so on, okay? So it turns out that we have a similar situation for the big L, okay? So we are going to essentially just sub in one of these capital letters up here for the L. So whatever you calculate your L to be, it's going to be a number. You're going to find it, okay, and match it up with the corresponding letter. So this letter goes into here. Okay, so these will pop up into that L notation. Okay, so you'll end up with things like a singlet S or a triplet P. Okay, those are the kinds of notations that you're going to end up with when you put together a term symbol. Okay, so that is the notation that we'll be using to make our term symbol. So this notation is the term symbol. Okay, again, there will be multiple, or there may be multiple microstates that will correspond to a single term symbol. Okay, and that's because remember we have for every L there's a range of m sub L values, right? And for every S there's a range of m sub S values. Okay, so you'll get sometimes multiple microstates that correspond to a single term symbol. Okay, so this is it for the initial mechanics of putting together an atomic term symbol and how we quote-unquote calculate the term symbol or designate the term symbol and account for that labeling. And then again, just reminding you why we're bothering to go through this process of adding this additional labeling system to our atoms. It's because when we look at the actual atomic spectra, okay, we would expect a certain amount of splitting just based on the electron configuration as we know it, okay, but in reality, we actually see a lot of additional spectral splittings that occur when we look at our atomic spectra, okay? That's going to depend on the resolution of the spectrometer that you use, Okay, so sometimes these splittings, so these are really close in energy. Okay, those might blend in together if you don't have a high enough resolution. Okay, so they might not always be apparent, but if you have the resolution in your instrument, you will see these kind of what would otherwise be unexpected energy splittings in your atomic spectra. Okay, so this new labeling, these term symbols, essentially allow us to account for this additional spectral splitting that we do see experimentally. Okay, and then, like I said, there's one more add-on that we can talk about later. That's our spin orbit or Russell-Saunders coupling, where we get even more splitting. Okay, so if we account for even more kind of couplings of angular momenta, if we couple the spin and the orbital angular momenta together as well, then we get what we call this fine structure or spin orbit coupling, and we get even more splittings here. Okay, so again, this is all stuff that we will talk about more as we go along, but this was just a quick introduction to the term symbol and the term symbol notation, and you'll get lots of practice doing some examples as we go along. All right, hope that was helpful. Thanks.